so that you have a good idea what to do. I expect a lot of work on this homework. Okay, work hard. And I expect a lot of different answers. Everybody's answers could be different. If your answers are all the same, that's a problem. All right, so the first problem, I guess it's supposed to have a number 1 here, but we forgot the number 1, so I have to fix it. But it is number 1, and the reason you can tell is because it's on the first page. It's a big clue. Okay, so algorithm complexity is given by a code. If you see this on a test, can you give me a simple algorithm that does this? Who can do it? Tell me. Okay, Zoe, what is this algorithm going to look like?
So one for loop with n.
One for a loop for n, actual work?
Yeah, for actual work. Twice the call of t to n divided by 2 and twice the call to t to n divided by 2.
Okay, so so did everybody hear what he said? Did you hear what he said? So it's going to be one for loop for n iterations, 2 recursive calls with n over 2. N is the parameter coming into the function, and 2 recursive calls to n over 3. Does it matter if the loop is in the middle, in the front, or the end? Does it matter? No. It matters for the algorithm, but it doesn't matter for the complexity. Okay? It matters for the algorithm, but it doesn't affect the complexity. So that's easy, right? Okay, so if you can take this math and write the simple fake algorithm that gives the same complexity, then if I give you the fake algorithm for a test, you should be able to come up with this math easily too, right? Okay, you've got to be able to go both ways. Okay, so the first thing I'm trying to do is I'm trying to get you guys to draw the recurrence tree for this algorithm complexity. So let's talk about what does the recurrence tree look like? On top you have what?
N.
On top you have level 0, which is going to have the complexity of n. And then now we're going to have how many branches? 4 branches. There's going to be 4 branches. The first branch will come down with what? And the second one, another. And then the next one, n by 3, and the next one, n by 4, right? So the n by 2 is going to do how much work? N over 2. N over 2. N over 3. N over 3. I'm giving you a lot of hints here, right? Okay. So draw the recurrence tree so you understand what's going to be happening. So you understand what, so we're going to have a branching of 4, 2 of these, and then each of them will perform the complexity of whatever problem size is giving linear relationship. Now, this tree is not full since it terminates on various levels. Does that make sense? Why? It terminates. Why does it terminate at different levels? Yeah. Which branches are going to be the deepest? Okay, these are going to be the deepest, right? So it's not going to be full. Full means what? That every level is completely filled. If there's one node on the level, then all the nodes are there that need to be there. For every level that exists, it must be maximally filled. So it's not full because it terminates on different levels. So we're going to use an upper bound tree to find the upper bound complexity of this algorithm. So that what I'm saying to you is I want you to, there is no height of the, well, there is a height of this tree. But the height is not even everywhere, right? Here it may be the longest and it's kind of like this. So what we will do is we will use an upper bound height, upper bound tree height. What does that mean? We will choose wherever the tree is deepest, the biggest height, for an upper bound. Because basically, if I assume the tree is as deep everywhere as it is at the deepest point, then I'm overestimating a little bit, which means I'm doing an upper bound. Okay. Try to find the geometric sequence and sum its terms. So that's your challenge. Okay? I think there's a C part. No C part. Too easy. All right. So part number 2. So number 2 here is, I think there are 3 ones here. For each complexity, determine the closed form using the master method if it applies. So you have to make sure that it applies. If it does not apply, use a simplified complexity which does not conform to the master method and determine the big omega complexity. Okay, so let's take a look over here. Hello. Does this look like it applies to the master algorithm? What's the problem? There's not one A and there's not one B. There are 2 of them. So, how many branches is this algorithm going to have?
3.
I don't know, you got 6, but okay, 3. Okay, 3. So 2 recursions with n over 4, 1 recursion with n over 2. Now, I'm looking for you to get the big omega. What does that mean? Lower or proportional bound. So your algorithm is either the same or it's higher complexity. So what I want you to do is I want you to switch this into master form, which means it cannot have 2 A's, cannot have 2 B's. It must have 1 A, 1 B, such that the resulting master form is going to be a omega. Okay? So determine its big omega complexity. Okay, I'll let you do that one. Okay? So take a look at these. So some of these are going to be a little more challenging than others. Take your time. Do the best you can. Do the best you can. I'm going to try to give you harder homework than tests. A lot harder. Because I want you to really work. Okay. Problem number 3. So now I want you to determine the following. So we have 2 parts A. Very interesting. That's A. That's A prime. I don't know. Okay, using limit, determine f of n if f of n, n log n, is an element of theta n to the 1/5 power. What's the 1/5 power? 1.5 power. What is that? That's 3 over 2. Right? 3 over 2 power. So what is this? This is 1 power times log n. So you're going to do it by limits. How are you going to do it? Ratio, right? Okay. So you're going to do the ratio, and then you're going to take the limit as n goes to infinity. Remember L'Hopital's rule if we need to use it, right? But only use L'Hopital's rule if it applies. L'Hopital's rule applies in the case of infinity over infinity. This is going to infinity, this is going to infinity. Then this is if this is going to infinity, it's trying to make this whole thing go to infinity. But this is going to infinity, it's trying to make everything go to 0. Which one is stronger? If this is stronger, it goes to infinity. If this is stronger, everything goes to 0. That's what L'Hopital's rule is. It's looking at the rate of changes. Okay. The next one I have determined by limits if f of n, n times log square n element of big O. Notice theta here. This is big O. It's different, right? Oh, I didn't know it was different. Yes, it's different. So just notice that subtlety. Don't try to just go, okay? So, and again, it's n to the 1.5 power. Recall that log square n is equal to log of n times itself. This is not the same thing. This is not the same thing as log n squared, which is 2 log n. Because this is log of n times another log of n. It's different. Does everybody understand the difference? You sure? Okay? I just don't want you to interpret it differently. All right, part C. So this one, use limits to determine if n 2 to the n is an element of what? Little o of 3 to the n. So we're looking for little o. What does that mean? We're trying to find out whether, remember, what is little o of 3 to the n? It's a set of functions that grow slower than 3 to the n. So we want to find out if n 2 to the n is slower growing than this one. Okay, so L'Hopital's rule. So I'm trying to tell you, you're probably going to use L'Hopital's rule. What is a to the x? What does this mean? What does this little mark mean? Derivative, prime, right? Prime. So a to the x, like 3 to the x. The derivative of e to the x is e to the x natural log of e. The derivative of 2 to the x is 2 to the x natural log of 2. The derivative of 3 to the x is 3 to the x natural log of 3. The derivative of any constant a to the x is a to the x natural log of a. Whatever that a positive constant is. Okay, so just a reminder, a to the x prime, derivative of that is going to be the same thing times ln a for any constant a. All right, so those are 3 problems. The last problem is the most interesting problem. I call this the thinking man's problem. You have to think on this problem. So I created this new special tree called the max-min tree. The max-min tree. Did you read this problem yet? Okay. If you search all over internet, you will not find the max-min tree. Because it only exists in my head. And even there, it's not very steady. Okay. So max-min tree, so basically it's a very simple rule. It's nothing very exciting, but it's a special tree. So a binary tree called the max-min binary tree. The tree has the max number of nodes at depth 0. Root 1, of course. Because the maximum number of roots you can have is 1. Okay, then, so you can start drawing the tree right now, right? The maximum number of nodes, you know what that looks like, right? Not complicated. Okay, so, and then the min at depth 1. So if we go from the root to depth 1, we have the minimum number of nodes. Well, what does that mean? How many different trees have that number of nodes? 2 different trees, actually, right?
Left and right.
You could have a left child or right, but you can't have both. Why not? Because then it would be a max-max tree. And it's a max-min tree. So from 1, the minimum would be 1 at level 1. So now we're going to level 2. Level 2 is going to go max again. So what are we going to have? So level 2 will have the maximum number of children from any node at level 1, but there's only 1 node at level 1. And then level 3 will be again another min, which means that the nodes above it will have the minimum number of children, but the nodes below it will have maximum number of children. So this will alternate, max min, max min, max min, max min. Okay? Yes?
Does it matter if the min depth has a left child or right child?
It doesn't matter. In some cases it would matter, but in this case it doesn't matter. Because all we're interested right now is counting the nodes at the levels. We're not counting anything like how many nodes are going in this direction or that direction. Okay, so that's a great question, but it doesn't. So the answer is not in this case. Okay, so I'm asking you to draw a min-max tree, a max-min tree of height equal to 8. Height equal to 8. What's the maximum depth? 7. What's the minimum depth? Also known as the root. Okay. So now, once you draw this tree, then you have a picture in front of your face. And I'm asking you to determine the formula for the number of nodes of depth d in a max-min binary tree. So now what I'm going to say, I'm going to say I have a max-min tree, and it has, how many nodes are at level 17? And I want you to give me a formula for that so I can plug it in and determine the number of nodes at that level. So you'll have to look at the tree and model how to get that number. So you look at depth 0, this many nodes. Depth 1, this many nodes. Depth 2, depth 3, depth 4, depth 5, 6, 7. Generalize in your head. Once you generalize it, you'll see 8. So you'll see 8. So you'll be able to. So you'll generalize. Try to see. Okay, if I use this formula, does it work for 3? Yes. Does it work for 4? No. That's not the right formula. How about this one? This also works for 3. Does it work for 4? Yes. How about 5? Yes. 6? Yes. 8? Yes. 16? Yes. It's probably right. Did I prove it? No. Is it probably right? Yes. Very unlikely it's going to work continuously like this, but okay. Does that make sense? So okay. And now the question.
Does it have to be a closed form?
Yeah, this will be very easy closed form. Now The last problem, I'm going to let you know right now, is going to be the most challenging. That's why I gave you an entire page to do the work on it, to see what you're going to come up with. So determine the formula for the average depth of a node in a max-min binary tree of height h. So remember, before you can solve this, because not everybody's a genius, you know, and when I have to solve a problem, I try to break it down and look at small examples to see if you can generalize. So you don't need height h right away. You can do on paper, do all the work. Once you solve it on paper, then you can type it in and put it into the Word document. But the bottom line is you want to have a height that's general. So the height could be, and again, what's a height? So in part number 1, what's the height of that tree? 8. So it literally has 1, 2, 3, 4, 5, 6, 7, 8 levels. Because remember, height is the distance to an external node from the beginning. So it's from here to here, it's 1, 2. By the time I get to 8, it's 7. And by the time I get to the first external null node, it's 8. So the question here is, determine the formula for the average depth. Now, you're going to need two pieces of information. You're going to need to sum the depth. You're going to need to sum the depths of the nodes. To get the average depth for each node, you have to add its depth. So that's going to be the numerator. So the numerator will be the total sum of the depths of the nodes. But then to get the average depth, you're going to have to divide by number of nodes. So that's going to be a second calculation. So you need to know. So for example, if I told you I have a max-min tree of height 8, hello, there it is up there. How many nodes does it have? Plug it into your formula. Does it come out perfectly? Yes. It does? Good. Now plug in 7. If you plug in 7, that's also up there. You can figure it out because 7 is 1 less than 8, so it's already up there. You can. It works there. It works there for 6, for 5, for 3. It's probably the correct answer. Okay. Now what's going to happen is you're going to see that the max-min tree has a different behavior in terms of odd and even depths because of the max-min, max-min, max-min. Right? So because of that, I give you a hint to set up the summation for... Now, the summation I'm talking about is not the number of nodes. The number of nodes is a relatively easy summation, relatively straightforward summation. You can get that. I think you understand what I'm saying. So I am giving you a hint about the numerator, the sum of the depths. You're going to find out that the sum of the depths varies between the max and the min levels. So the levels are max, min, max, min, max, min. Or if you want to think of it, even, odd, even, odd, even, odd, even, odd. The even levels start with a root and level 2 and level 4 and level 6. The odd levels are 1, 3, 5, 7, etc. So you can set up the summation for the total depths of all the nodes. And you're going to find out that when you set up the summation, it might give you something that's difficult to make a closed form. Because the behavior of the odd and even levels is different. But all the even levels are the same, and all the odd levels are the same. So we can split this into even and odd depths, the max and min, the max and the mins, which are odd and even. Split them in half. And when you split them in half, then you'll be able to more clearly see that these summations are not too difficult to solve. They're going to be something that we've done in class, something that we've done in one of our mathematical models, for sure. Okay? And those you'll be able to put into a closed form and then combine them together. So after you do this, if I say, for example, a maximum tree has a height of, for example, 18, I should be able to plug it directly into your formula and find out the average depth of a node. Okay? So that's your job. Okay, and again, we're looking for your maximum effort, not your... Okay, so the master method we talked about last time has a formulation that you only have to have one A, which is 1 or higher, and 1B, and that has to be 2 or higher integers. So that's the restriction that we have. All right, and then we looked at the different methods, and so we compare f of n with n to the log b of a, and we notice that if we have n to the log b of a is growing more quickly than f of n, then the whole thing is n to the log b of a. And what that means, and you'll see it in a second as I show you on my notes after I finish these, is that what's really going on is the work as you go down is increasing exponentially. And so what that means is by the time you get to the bottom level, the amount of work at unity is exponentially bigger with every single level that came before it, so the complexity is owned totally by that bottom level. In the second case, we looked at this example when the amount of work being done on each level is proportional, or pretty much the same on every level. So in that case, our T of n is going to be our function times log of n to the power of k plus 1, whatever k was when we set up this equivalence. And the third case, the last case that we looked at, is we're looking at a situation where basically f of n is bigger than this one, because we have to add this positive epsilon to get equivalent. So this is smaller, this is bigger. And we're saying basically the whole complexity is theta of the level 0 actual cost because the amount of work is decreasing with each level, which is satisfying the regularity condition that says basically that the amount of work at level 1, okay, is actually less than the amount of work, so the work is decreasing at level 1. Okay? So did we look at this example yet? I forget if we did or not.
Yes.
I think we did, okay. Yeah, we looked at this one, and we looked at this one also? Okay, good. I thought we did, I just want to make sure. I think that might be the last one we stopped at. Here we go. Okay, so let's take a look at this one right here. What's the value of A, coefficient A?
4.
So 4 and b is 2. So again, we have n to the log b of a is going to be n squared, and f of n is n cubed. So now we're checking what? We're checking the regularity condition, which is going to be 4 times n over 2 cubed must be less than c n cubed for some c which is less than 1, between 0 and 1. Okay? And is that true? So that's going to be n cubed over 8, right? N cubed over 8 times 4. So it's n cubed over 2, 1/2 n cubed. So for any number that's c of 1/2, you can see what's going on, that the work is decreasing. This time it's decreasing by 2 actually, right? Because half the work. So it fits the regularity condition. So what we're seeing is that the work done at level 0 is exponentially decreasing. So therefore, by the time you get to the bottom level, all the work in the entire tree is proportional to just level 0. Now in this example here, we have the method does not apply. So we have 4t of n, so we still have a is 4, b is 2, n to the log b is n squared, and f of n is n squared over lg of n. So what's the problem? First of all, case 2 doesn't apply, right? Case 2 doesn't apply, because the power of the LG here is -1, right? Because 1 divided by LGN, which is LG n to the -1 power, so that's not appropriate. So case 2 does not apply. What about case 1 or 2? Now, the reason it doesn't apply, because for every constant which is positive, we have n to the epsilon is equal to little omega of LGN, which means that this algorithm is not doing what? What's different here? We don't find a polynomial difference between them. We can't find the polynomial epsilon. So in this case, it doesn't apply. All right, that's a special case. I'm not going to try to give you that kind of stuff, but basically, you just have to be aware. All right, so the idea of the master theorem is this, right? So this is f of n, and then a is the coefficient, so we have a branches, each one of them getting n over b. Then we have a for each of the branches in a, they have a, so it becomes a squared branches, etc. And then they have n over b divided by b again. So eventually, as we divided by b, eventually we're going to go to unity. And of course, in the case of the master algorithm, the tree is full. Because everyone is getting the same amount of work at every level, so they're going to go to unity at the same time. And that's what gives it the power that you can do the theta complexity. Okay, so you can see what's going on here. So here we have a to the 0, f of n, right, divided by b to the 0. This is a to the 1, f of n over b to the 1, a squared, f of n over b squared, etc., 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 all the way down to unity. Okay, so the height of the tree is always going to be this, and the number of leaves is going to be a to the h. This is h, but h is equal to log b of n, and that's why we have a to the log b of n, because that's simply the number of leaves. And a to the log b of n can be written by switching the a and the n into n log b of a. That's the value. So basically, essentially, that's the number of leaves down here, is this quantity, or this quantity. But this quantity is a little bit easier to work with, because this is the polynomial complexity we're talking about. Okay, so the case 1, the weight is increasing geometrically from the root to the leaves. The leaves hold a constant fraction of the total weight. If the weight is increasing, therefore the leaves drive the complexity. Case 2, the weight is approximately the same. In that case, the sameness is multiplied by the log to base b. In case 3, we have the weight decreasing geometrically from the root to the leaves, so therefore the root, or the level 0, holds the constant fraction of the total weight. Okay, so that's it. So I'm going to give you just another shot at the master theorem with another set of notes. These are my notes. They're pretty straightforward. So I want to show you that. They're not as fancy as the other notes, but they're straightforward. So that's always good. All right, so the master theorem, that's our setup here. We start at the root and split the recursion into a branches. Level 1 has 1 node, level 2 has a nodes, level 3 has a square nodes, etc. The height of the tree h is when we cannot split in any further because we've come to unity or single element. The h function is a function of n, so h is equal to log base b of n. So from number 2, we see that the number of nodes at the bottom level is a to the log b of n, which is equal to n to the log b of a. And so this is case 1. It's a different way of, a little bit of a different way of looking at case 1. So if we have, if we have very similar, so now we have a is equal to 4, b is equal to 2, and n is linear. So it's an example similar from the book. So we have n squared is n to the log b of a, right? So that means that the amount of work at the leaves appears to be higher than the amount of work being done at the root level, which is level 0. So the function of n is growing polynomially slower than this one for epsilon equal to 1. And you can see what's going on here is that we're going to have f of n is going to equal to n. Then it's going to be 4 times n over 2, which is 2n. Then it's going to be 16 times n over 4, which is 4n. Then it's going to be 64 n over 8, which is 8n. And eventually it's going to go to n squared. You can see that n squared is actually the number of leaves. Right here, you can see so what's going on with the work? The work is increasing exponentially towards the bottom. So the cost is increasing geometrically on each level, and so therefore the complexity is going to be right here. Because all these n values are simply part of this geometric one. What's the constant as we go down? How much more work is at this level than the previous level? 2. 2 times. So 2 times. So 2 times. All right, so you understand how that works, right? So think of the tree. You have 1, 2, 4, 8, 16. So 16 is twice as much as 8, is twice as much as 4, twice as much as 2. So basically this one has the order of the tree. If you have a tree that has 1,023 nodes, 512 of them are down here. And it's half of it. So 2 times this is the whole thing. So therefore, this is roughly showing me that the amount of work here is essentially 2n across the tree, or 2n squared. That means all these levels here are going to be approximately the same as n squared, because it's doubling each time. Actually, it's going to be a little bit different. Levels are, even though it's 4. Okay? So now let's take a look at the case where, so all we did here was we switched the f of n to be from n, now it's n squared. So in this case, we still have n to the log b of a is n squared, and we see what's going on in the work. So the work is going to become n squared, and then we have again, well, look what we have. See what's going on here? N squared, n squared, n squared. So we have n squared at every single level. But the tree is full, and its height is
Log of n.
Log of n. So our complexity is going to be n squared log n. Case number 3. Now case number 3, I just increased this one, kept this same, increase this to n cubed. If this is n cubed, then f of n is n cubed, n to the log b of a is n squared, and I just plug it to see what's going to happen. So it's n cubed, and then it's going to be 4 n cubed over 8, 16 n cubed over 64, 64. Now look at the amount of work here. So n cubed over 2, over 4, over 8. What's going on with the work as it's going down? It's decreasing. So that means the work being done at the top level is going to be about the same as it's done on all previous levels. Which means that all the work. Now, does this function fit the regularity condition? Does it fit the regularity condition? Regularity condition says that the work at level 1 must be a constant fractional part of the work at level 0. Yes or no? And what's the constant that we can use? What's the biggest constant that we can use between 0 and 1? 1 over 2. 1/2. Because you can see that the work is decreasing, and it's n cubed over 2. So for c equal to 1/2. Okay? Does that make sense? All right, so that's it. I just wanted to show you this so you can sort of see what's going on here. So in order to use it, you've got to make sure that the work here is decreasing. That's it. All right. All right. I'm going to look at an algorithm called quicksort. I think I have another set of slides for that. Let me just check for a second. Quicksort. Okay, so we'll start with these slides, then we'll jump to my slides. Okay, so how many of you are familiar with quicksort algorithm? Only a few people? Okay, so some people have Ever heard of it? What makes quicksort a pretty famous and a pretty useful algorithm is the fact that it has a really nice complexity for big problems. But that's the good news. The bad news is it has a bad worst case complexity. Okay, it has very good best case complexity, but very bad worst case complexity. When I say very bad, I'm talking about n squared, kind of like bubble sort and insertion sort, where it's not really good for really big problems. But it turns out it has a very good average complexity. And average complexity is essentially the same as the best case complexity. So that's what makes it a useful algorithm. It has the same complexity as merge sort, but it doesn't have this so much overhead as merge sort. Merge sort had the overhead of having to have the special array for merging, okay, and all that stuff going on. So that was kind of slowing it down. Quicksort doesn't have that issue. So let's learn a little bit about the quicksort. Quicksort was developed by fellow C.A.R. Hoare in 1962. And I always like to tell the story is that, you know, people think it's one of the greatest algorithms ever created. And so they're asking him, you know, what other kind of great algorithms did you come up with? Because this is such a wonderful, you know, and he goes, well, actually, this is really the only algorithm I really came up with. He did it because as engineer, back in 1962, there weren't a lot of books to go to how do you sort. He needed to sort some data. And so he came up with the idea of doing this quicksort because it was the first thing that he thought of. Which is, if you look at it, you're going to say, well, it's probably the last thing I would have thought of, but it's really clever. That's what makes it interesting, is that it's still famous otherwise. So C.A.R. basically, he came up with something. This is in the class of algorithms that we'll call divide and conquer. We'll look at other divide and conquer algorithms. And what happens is it sorts in place. So sorts in place means that the data never leaves its array or its locations. That's true for insertion sort, but insertion sort is theta n squared. Average case, best case, well, best case, not best case, but average case, theta n squared. But merge sort is not in place because it basically every time you partition the arrays, you have to sort them, so you have to sort them into another array and then copying them back to the original array so you can continue processing. So merge sort has some problems in terms of doing a lot of extra copying. Although, the good thing about merge sort is that its worst case complexity is the same as the what? Worst case is the same as its average and same as its best case. It really doesn't move, but it has a lot of overhead costs. So if you're sorting something that requires, for example, 1 gigabyte of space, then merge sort will require 2 gigabytes of space. So it will require the doubling of your original space for the merging part of it. So that's, and of course it's going to have to copy it in there and copy it back. So there's a lot of copying. And guess what? That copying takes time. So sorts in place means that in quicksort the data never leaves the array. Okay? And it can be very practical, very useful, very efficient with some tuning because there could be some problems with quicksort because its worst case is theta n squared, and that's bad. But its best case is theta n log n, and its average case is also theta n log n, and the key to see how that happens is what we are doing here in this course. Okay, so the idea of quicksort is to essentially do a partition on the array. And so what you see here is some value x. So let's say the value is 18, I don't care, some value. So what this means is that everything to the left of this one must be less than or equal to 18. Now, these numbers do not have to be in order. All we want to do to partition is to place one element into its proper final location, and everything to the left must be less than or equal to. Now this case here, this really should read greater than, so this should be greater than x, which means that these are all values bigger than 18. So 19, 20, 21, 22, 30, 40, 50, all those numbers. And again, these numbers are not in order with themselves, they are just partitioned around this 18 or this x value. And these are 18 or less, because you could have duplicates. So we will divide, number one, we'll divide the array by partitioning the array into two subarrays, the left part and the right part, around an element called a pivot. So A will be kind of like a pivot, like if you have a balance, right, pivot. So these are the smaller values or bigger values. So we're going to have a pivot x such that elements in the lower are less than, elements are here are greater than. So less than or equal to, greater than. If you put equal here, you got to get rid of equal here. If you put equal here, you got to get rid of it here. You can't have it both ways. It's not as efficient. Okay. So recursively, we'll sort the two arrays, and the combination of them is going to be trivial. Now, the partitioning is what is the actual cost. Everything else is recursive cost. The partitioning is the recursive cost. Now, if you think about it, we have one algorithm that we talked about sorting-wise that does something like this. It does a partition so that it places one element exactly in the right location. What algorithm is that? Bubble sort. So if I do bubble sort and I bubble up, let's say I'm bubbling from the lowest to the highest, then the smallest element will end up here. And I will have partitioned the array into 0 elements less than me and n minus 1 more than me. In fact, every time I do bubble sort, the smallest element on the first pass will always end up at the top. Always. So the partitioning will always be 0 elements less than me and n minus 1 greater than or equal to me. So that means after I finish the first pass, this partition is finished because there's nothing to do. It's an empty partition. But this partition is size n minus 1. Therefore, I have to do n minus 1 work again. And again, what's going to happen here is I'm going to get one more element out, which means that above, I'm going to have a 0 partition, which is nice, but then I have an n minus 2 partition. So I will keep getting n partition, n minus 1, n minus 2, all the way from n all the way down to 1, and the summation of that is going to be theta n squared. So that's why, okay. Now, so this one is kind of similar because it also places one element, but the difference between quicksort and bubble sort is quicksort does not choose to put the smallest element at the beginning. It chooses a random element to be placed wherever it belongs. So if the element is chosen such that that element goes around the middle, then we have about half above it and about half below it. So rather than having 0 and n minus 1, we have n over 2 and n over 2. And if this happens again, we're going to have n over 4 and n over 4. And n over 4 and n over 4. Right? So n, 2n over 2s. Put the random pivot in the middle, then you have 2n over 4s. Well, if the pivoting algorithm is linear complexity, that means when my level 1 comes in with n, to pivot that element into its location is theta n. It takes n operations proportional to get that element in the middle. Wherever that element doesn't have to go here. It might go here, it might go here, it might go here, but it's not likely to go here, because if there are 1,000 elements here, there's only 1 in 1,000 chance it's going to end up here. 1 in 1,000 is going to end up here. Where do you think on average it's going to go? It's going to tend to want to go in the middle. Right? So, as I divide the original problem of size n, the partitioning costs me n at level 0, because I have n elements and partitioning is linear. If I hit the middle, then I have 2n over 2s, which means the partitioning here plus here will be n over 2 plus n over 2, which will be a total of n across level 1. And the 2n over 4s on each side will produce 4n over 4s, and the summation of n over 4 times will be n again. So the partitioning at every level is n. 1n, 2n over 2s, 4n over 4s, 8n over 8s. So it's n, 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 n. The question is, how many n's are we going to end up with? And the answer is, we'll end up with as many n's as there are levels. And since we're creating halves, quarters, eighths, 16, 32, 32nds, 64ths, we're going to do this log 2n number of times. So if we can hit that pivot in the middle, then our height of our recursion tree will be log 2n, or LGN, and the work across our levels will be n. And so the complexity will go to LGN. But that's only if the pivot goes in the middle. And we're saying that's not guaranteed. It could go anywhere. In fact, the probability is equally likely that it'll go anywhere. So let's look at the partitioning. So this is the algorithm. So the idea is that we're going to try to play around with these indexes I and j and move them to a position where we can make a determination where the pivot is going to go. So my elements are coming in. The array A includes indexing from P to Q, first element, last element in the particular level. So this could be the first element and the last element for level 0, right? Then after the pivot, P and Q will be the first and last to the left of the pivot, and first and last are on the right of the pivot. So the first thing we do is we take out the first element and we put it into X. So we choose arbitrarily the first element to be the pivot. Okay? Now that's going to be X. And then what we do is we set I, our first index I, equal to exactly P. So we set I equal to the index of P. And now we're going to do some looping. So we're going to do a loop. We're going to say for J is equal to P plus 1 to Q. So P plus 1 means now I'm going to go, index is going to start at the second element, past the pivot, and we're going to try to go all the way to the last element that's in the array. And I'm going to find out. So now J is going to be equal to that second element. So we start I is equal to here, and J initially is equal to the next element. And what I'm trying to do is I'm trying to push I and J to a position where I can determine the location of the pivot. So if AJ is less than or equal to X, then I is moving to the right. So imagine, for example, that X is equal to 5 and the next element is equal to 4. So I is equal to P, J is equal to P plus 1, X is equal to 5, and the next element over is equal to 4. So is AJ less than or equal to X? Is AJ less than or equal to X? Yes, because 4 is less than or equal to 5. Therefore, what's going to happen? I goes to on top of J. Well, let's see what's happening here. That means the 5, where I was, and now it stays there, and now the I is where the 4 is. Well, if you think about it, the 4 belongs in the left partition of numbers that are less than or equal to 5. That means the 5 cannot be any to the left of that I value. The I value will delimit where elements are less than or equal to the pivot. So now, after I did that one, okay, I'm going to set this equal to here. And I'm going to continue pushing the value as AJ is less than or equal to X. If the next value, for example, is another 5, now J is equal to 2 elements passed here. If this element is 5, and 5 is less than or equal to 5, then I, once again, is going to get moved over. Okay, let's look at an example of how this is going to work. So initially we have I and J. Which one is the pivot? So 6, why is it the pivot? Because it's the first one. Isn't that biasing it? No, because the elements are assumed to be in random order, so therefore the first element is as random as any other element. So we choose arbitrarily the first element as a pivot. So now, does the 10 belong in the left partition or the right partition? Okay, so let's see what's going to happen here. So J goes forward. Now, does the 13 belong in the right partition or the left partition? So J goes forward. Now, does the 5 belong in the left or right? Okay, so in order to do that, notice that what we need to do is we need to make a space for the pivot. So what we're going to do is we're going to take the value and we're going to be able to swap. We're going to take a swap. What are we going to swap?
5 and 6.
13.
Well, basically, we're going to, okay, so watch what's going to happen here. So we're going to swap. 5 and 10 are swapped. The pivot stays here, but notice that when the swap occurs, I is moved to the next location. So initially I was here and J was here. I was here and J was here. When we have a violation, we know that I is the last element in the left partition. Since we have now found a violation here, we are saying what? This element belongs in this partition, and this element could be moved to that partition. So we swap the 5, and which is the jth element, and the I plus first element. And that's why we have this situation here. Does that make sense? So notice that I is again showing you that 2 elements will be in the left partition, and at least these 2 elements in the right partition. So what does J do now?
J starts from 6.
J can consider the next element, right? And what do we do now? Should it be in the right partition or left partition? It's going to be in the right partition, so we're just going to go forward. How about 3? 3 belongs in the left partition. So therefore what we're going to do is we're going to take the element here, which is in the wrong partition, and we're going to take the element here, which is 13, and move it into this location, and 3 here, and I goes to
3.
the third location. So we switch the 3 with the 13. Notice that now we have 3 elements in the left partition, and at least these 3 here. So now we're going to move J to 2. 2 again belongs in the other partition, so we'll switch the 2 with the 2 with the 10. And when we do that, then notice that 4 elements are in the left partition. And now we will go to, look at this one. Is this one in the proper partition? Okay, so in that case we're going to go next, but when we go to the next one, we're going to be off the array. So that means we have decided that the partition ends here for the left side and begins here for the right side. Now the question is, where should the pivot go? The pivot should go into index because I marks the end of the first partition. So now the 2, and again, so now the 2 can be swapped with the 6. Notice that the 6 is now the x value, which is in the proper location. Is 6 ever moving? Nope. It's done. So divide and conquer. So we divided the array initially, and we conquered one element, and we split it in half. Divide, and then we conquer the remainders. Notice that we didn't exactly go in the middle, but actually this happened the best it could for an array of 8 elements. This is the best we can do, is have 4 and 3. So that's really pretty good. So now what are we going to do? So that's called a partition. So that's what partition looks like at level 0. So now what we will do is notice that these elements are less than or equal to 6, but not in order. And these are more than 6, but not in order. So we're going to quicksort the left side, and we're going to quicksort the right side. What does that mean? That means we're going to partition the left side and recurse with the left and right, and we're going to partition this one and recurse with its left and right. And until we're down to unity, we're going to continue doing that. And so as long as the pivot is falling towards the middle, it gives us a feeling that what? That we're going to get close to that n log n performance. because each of the partitions is good. Remember, the partition here that we did is theta n. Why? Well, because if you look at the partition, we started I and j over here. Okay? And j basically kept moving every single time. Then we might do a couple swaps, okay? But j kept moving, so the movement of j basically shows you that it's always moving. And when j comes to the end of the array or off the array, and it can happen in theta n, you're done with that partition. And at that point, you just do a single swap and you're done. Questions? And so this is a pseudocode for quicksort. So you want to do a quicksort of the array A from starting index P to ending index R. P less than R means you have what? You have more than one element. Lower limit is less than the upper limit. That means they're at least one away from each other, at least two different elements. So two or more elements. One element for quicksort, you're done. 0 elements, you're done. Okay, so at that point, if we have at least 2 elements, then we'll do a partition, and partition will return Q. What is Q? Q will be I. Q will be the index. So in this case, if we count 1, 2, 3, 4, 5, 6, 7, 8, we're going to return 4. And so what's going to happen is, then we will, since Q is equal to 4, we will do a quicksort from 1 to 3, and another quicksort from 5 to 8. Which is, yeah, because remember, this is going to be 1 to 8 in our case, right? 1 to 8, 4 comes back as Q, so we go 1 to 3 and 5 to 8. The initial call here is going to be the array from 1 to n. 1 for P, n. But as soon as we get this 4 for Q, then we're going to go, P is going to be 1 and R is going to go 3 in this recursion, and here P is going to be 5 and R is going to be 8 for the second recursion, level 1. And of course those will then cause another recursion level. So if you look at this, which is the pivot for the left side? 2. And so what's going to happen, 2 is here, that's I, J is going to go here, J is going to go here, J is going to go here. So we'll switch the pivot with I, 2 with 2. Yes? Okay, then we'll go to the right side. How many elements are left in the right side? 2, which is only the 5 and the 3. So that's P, that's Q. I goes here, J goes here. So what happens here? So I goes here, right? And then J goes off the array, okay? And we swap 3 with 5, and we're done. So now we go back up recursively, and we come back here, which is the pivot in the right side of level 0. 8. 8. So what's going to happen here? I and J, 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 J. So pivot is swapped with I. Boom. Now the remainder is here. 13 is the pivot. What's going to happen here? So all the elements, so these elements are going to be 13, 10, 11, 13 is the pivot, so where's 10 going to go? So it's going to get swapped 10 and 13 and then swapped again. You get the idea, right? Okay, so that's the partitioning. Okay, so now I'm going to do an analysis. Let's see, I'm going to... Worst case analysis. Worst case analysis is an analysis like this. So basically, remember, every level does n work. Because, right? However, if we partition and we get, for example, only one element here but everything else here, then we have n minus 1 work here, and we only reduce by 1, and n minus 2, n minus 3, n minus 4. So the worst case is basically always put the element on an end. And so you always have only a reduction of 1 on one partition and no work at all on a second partition, but that 1 is a killer. So T of n is equal to T of 0. which means the left, so for example, if I put the smallest element, the element at I back into I, then nothing is to the left of I, so t of 0 to the left of the left, but t of n minus 1 for the right of the partition. And then theta n is the partition at that level. So that gives us theta 1, that's unity here, t of n minus 1 plus theta n, which gives us t of n is equal to t of n minus 1 plus theta n. This can be solved easily by, how do we solve this? Is this a master algorithm approach?
No.
No, because we're not dividing. But we can do repeated substitution. Okay, repeated substitution. So basically we would have t of n is equal to t of n minus 1 plus n. And then this would be saying n minus 1 plus, right? N minus 1 plus t of n minus 2, et cetera, et cetera, et cetera. And then we basically are summing n minus 1, n minus 2, n minus 3. We get n squared, which is theta of n squared. So the worst case is theta of n squared. The question is, when does that worst case occur? When do you pick a pivot and it goes right back where it belongs?
Smallest
Every time.
Smallest element is the pivot.
So if the smallest element is here, it's going to go up and going to go back down. And now I have this. Now the pivot again goes up and down. That means it belongs here. Belongs here, belongs here, belongs here, belongs here. So what is this case? If the array is sorted, we have a disaster, because basically what we're going to do is we're going to get to the n squared case. Now how likely is that? I have no idea. Maybe the data you get is 99% of the time sorted, so it's very likely. Maybe you get totally random data all the time, so it's extremely unlikely. I don't know. What's the probability of that? P. What's the value of P? I don't know. I know it's between 0 and 1.0. But that's a situation that you have to be aware of. Okay, so the worst case recursion tree looks like this, right? So t of n, and then we get t of 0, and then we have this n minus 1, and then again we split t of 0 and n minus 2. And so you see what's going on here, right? So we have n plus 1, n minus 1, and n minus 2. So we're summing n from 1 to n, and it's going to be quadratic. So k goes from 1 to n. Here's 1, here's n. Best case analysis. We like best case. It's so optimistic. It's like people who play the lottery. You think they play worst case analysis? I just heard of a horrible commercial for the lottery. This fellow says, I played the lottery last week, and I told my wife is like, why are you getting dressed up in this fancy clothes? I said, I'm wearing my fancy clothes because I'm going to win the lottery today. And guess what? He won the lottery that day. And he was all dressed up to receive his check. That's a great marketing scheme. It's completely crazy. Does such a person exist? Yes. I bet you he gets dressed up every time for the lottery. It'd be very, very unusual for him to really have this idea that it's going to work out. But best case is useful for analysis, especially if we found out that the average case is approximating the best case, or is essentially the same order of magnitude. So if we're lucky, the partition splits the array right down in half. And of course, we can do that analysis with k with n equal to 2 to the k minus 1. What happens is if you have, for example, 31 elements, which is 2 to the 6 minus 1, 2 to the 5th minus 1, then you're going to get that one element, and then you're going to get, and 2 to the 5th minus 1 is 31. Take that one element out, you're going to have 15 and 15, which is 2 to the 4th minus 1. Take that middle element, and you have 2 to the 3rd minus 1, which is 7 and 7. 3 and 3, 101. So that's 2 to the k minus 1. So in that case, what we had was we're lucky, and so we always get about half the problem twice, left half, right half, and this is our partitioning cost. So that is simply, we can solve this by master, because here we have a and b are both 2. N to the log 2 of 2 is n to the 1. Okay, so that's going to be n to the 1, and f of n is n to the 1, so therefore we have n LGN. So that's the best case. That's the lucky case. Now, you've heard of the max-min tree, the very famous max-min tree. Also, we can have lucky-unlucky. So, for example, if we're lucky partitions, what if we split always 1/10, 9/10? That's pretty bad, right? You think it's pretty bad, because basically, if you split 1 or 0 and t of n minus 1, that's the worst case. But what if we have, so for example, if we have 1,000 elements, we're going to get 10%. What's 10% of 1,000? 100 and 900. And from this 100, we're going to get 9. We're going to get 10 and 90. And from that 9, and from the 10, we're going to get 1 and 9. You get the idea, right? So that looks worst or almost worst. It looks pretty bad. So if we split 1/10, 9/10, then we have t of n is equal to t of 1/10 n plus 9/10 n plus theta n. Right? Everybody agree with that? So let's go to the tree. So the tree gives us this. Right? So c of n, now what's this going to be? 1/10 Cn, 9/10, and like this. So this is going to be 1/10 of this, 9/10 of this, 1/10 of this, 9/10 of this, and it's going to continue. So finally going to get to unity. Now this, of course, it's 1/10, right? And 9/10, so which one's going to go faster to unity? 1/10. It's going to go longer, right? But look over here. The height of this tree is log to 10 over 9 n. Which means that the height of this tree is still logarithmic relationship to n. Now it's not log of 10, it's 10/9, which means the number will be bigger. Because if n is, for example, 1,000,000, 10 over 9 has to be raised to a much higher power to make 1,000,000 than 10. 10 to make 1,000,000, the log of base 10 of 1,000,000 is 6. But the log 10 to the 9th of 1,000,000, well, that might be, I don't know about 1,000,000, but it could be a much bigger number. Maybe 50 or 60, I don't know. We don't know. We can figure it out. We have calculators. We know how to use them. But, so it's basically happening that our complexity is still n log n. So n log n. So it's called lucky. Okay? So it's not we never get the worst case. It just seems that way. You can see here that n log 10n and n log 10/9 n plus big O of n is the value here. So basically you're always going to be, at the best case, here's the worst case. It's someplace in the middle, right? But even the worst case, the upper bound is going to be logarithmic, n log n. Okay, now here is our lucky unlucky. Lucky unlucky. So lucky means that we have, lucky case we have 2 unlucky cases of half, and unlucky means we get nothing on one side and everything on the other side. So we'll alternate lucky unlucky. So the lucky one will split evenly twice and partition. Unlucky will split nothing on the left and everything on the right, or nothing on the right, everything on the left, whatever. And again, a partition. So you can see as we do this recurrence, 2 times the lucky plus theta of n over 2 plus theta n. We end up simplifying here, and we still get lucky. So it seems that it's very difficult to really mess up very badly with quicksort. But these are contrived examples. Lucky, unlucky, lucky, unlucky. Max min, max min, max min. Very unlikely, but might give you some insight into some real behaviors. So we're really interested in something randomized. All right, so we're really more interested in seeing what's going to happen in real cases, on average, where partitioning essentially can happen anywhere. And I think we're a little bit out of time at this point, but I'll give you sort of the idea of what we're going to be doing. So the idea is something like this. So our analysis of average complexity of quicksort will be something like this, and it's very interesting. So basically, we know that our partition could put the pivot here, and therefore we have t of 0 and t of n minus 1 as the next level. And our partition could put it into the second element, which means we have t of 1 and t of n minus 2. Which adds up to n minus 1, right? Or it could be here, which would be 2 and n minus 3. Or it could be here, 3 and n minus 4. It could be anywhere. If it's the last position, it's going to be n minus 1 and 0. So actually, this end and this end, they're kind of symmetrical. And we can find out the complexity of every single one of these possibilities from any one of the pivot locations. Any one of the pivot locations. The question is, which one is actually going to happen? And the answer is we don't know. If we assume, with randomized data, that the pivot is equally likely to go anywhere, then we can find out, and if that's really true, then we can find out what is the expectation of the complexity of quicksort. That means what is the average complexity of quicksort. And so we'll do that by simply looking at all the possible ways that we could split and average their complexities, and that average complexity will be the average complexity of quicksort. Okay? So we'll do that on next time. So now you guys have lots to do for homework. Okay?